Hey, it's your bro. Hope you're doing well. And in this video, I'm going to explain the quicksort algorithm in computer science. Yep. So sit back, relax, and enjoy the show. Alright, quicksort. Here's how quicksort is going to work. We need an array or some other type of collection. I have a simple unordered array. What we do is that we'll pass our array as an argument into a quicksort function. After passing our array as an argument to the quicksort function, we need to pick a pivot. There's different variations of quicksort. We can either pick a pivot at the beginning, the middle, or at the end. But with most standard quicksort algorithms, we will set the pivot to be at the end of our array. What we're trying to accomplish is that we need to find the final resting place of our pivot. Where is this value going to be? And taking a look at this, that would be right about here. But we don't know that yet. So to find the final resting place of this value, our pivot, here's what we can do. We will declare and use two indices, j and I. J will begin at the start of our array. I will be one less than the beginning of our array, and that's going to be important later. And we'll need the help of a temporary variable so we can swap some values. All we're doing is checking to see if the value at j is less than our pivot. If it's greater than our pivot or equal to our pivot, we ignore it. 8 is greater than 5, we ignore this value, and then increment j by 1. So during that last iteration, I did not come into play yet, but it will this round. Again, we check to see if this value is less than our pivot, which it is. What we do now is increment I. Then what comes next is that we swap these two values, I and j. And we'll need the help of a temporary variable. So take the value at I, assign it to temp. Take the value at j, assign it to I. Take the value within temp, assign it to j. Then we can move on to the next iteration. Increment j. We check to see if the value at j is less than our pivot, which it is. If that is the case, we increment I, swap these two values. We'll repeat this process until j reaches our pivot. Then we can move on to the next step. Here's the next step after our index j reaches our pivot. We now know where the final resting place of our pivot is going to be. It's I incremented by 1. So we will increment I, then swap the value at index of I with the value at our pivot. Our pivot is now within the correct place. An easy way to tell is that all elements to the left of our pivot should be less than our pivot, but they're not necessarily going to be in order, and that's fine. They'll be organized later. All elements to the right of our pivot should be greater than or equal to our pivot. And like I said before, they probably will not be in order. The important thing is that elements to the left should be less than our pivot. Elements to the right should be greater than. That's how we know the pivot's in the correct place. Now the next step, we're going to create two sections, two partitions. The first partition will be all the elements from the beginning of our array up until our pivot, but not including the pivot. And our second partition will be all the elements after our pivot until the end of our array. Quicksort is a recursive algorithm. We need to pass these partitions as arguments into the quicksort function. Remember that the quicksort algorithm is a recursive divide and conquer algorithm. But unlike with merge sort, we create new subarrays. With quicksort, we will be sorting these arrays in place, but we need to keep track of the beginning and ending indices of these partitions. And then it's just a matter of repeating the same steps over again, but we're going to instead use these partitions, sections of our array. I'll give you a quick demonstration of what the quicksort algorithm is going to look like to completion. And that, ladies and gentlemen, was your visual representation of the quicksort algorithm. Let's code our own quicksort algorithm just to solidify our understanding of this topic. Alright people, let's create a quicksort function. You'll need an array to work with, place some random numbers within that array, and then some way to iterate and display the elements of your array. I'm just using a simple for each loop. So after running this, of course, our array is not yet sorted. So before we display the elements of our array, let's invoke a quicksort function, which we still need to declare and define. There will be 3 arguments: our array, and the beginning and ending indices of our array. So that would be 0 for the beginning. Then to find the ending, you can just say array.length minus 1. Let's declare this function. Private static void quicksort. And let's rename some of these parameters. We have our array of integers named array, and this will be the starting index, and this parameter will be the ending index. So we have indices start and end. Now the base case, this will use recursion, will be if end is less than or equal to start, then we will return. And this is our base case. Eventually, we won't be able to divide our array any further, so that's when we stop and return. With our quicksort function, we'll need the assistance of a helper function that we will name partition. Let's copy our function declaration, paste it, and make a few changes. So this will return an int, the location of our pivot, and the function name will be partition, and the parameters are the same. At the end of our partition helper function, we'll return I. I will be the location of our pivot, but we'll get to that later. Okay, so within our quicksort function, we'll need to find the location of where to pivot. Int pivot, and the partition function will be in charge of that. Partition is going to sort our array and find the pivot. So all elements to the left will be smaller than our pivot. All elements to the right will be larger. So pass in our array. We're sorting our array in place. There's no need to create any subarrays. We'll just pass in our original array, as well as the start and end. After we figure out where our pivot's going to be, we can pass in each partition recursively back into the quicksort function. So again, we will invoke quicksort, pass in our array, the start of our left partition, and the ending of our left partition. And that is where pivot is, -1. We do not want to include our pivot, and then we will need to use quicksort on the right partition. Change start to pivot +1, because the pivot is already in place. And then the end of our array. In this variation of the quicksort function, we will say that pivot is at the end. It will always be at the end to begin with. Int pivot equals array at index of end. We'll need two indices, I and j. We'll create index I equals start -1. And then we will iterate through our array. And this is where we will declare int j, our second index. Int j equals start. And we will continue this for loop as long as j is less than or equal to the end of our array -1. Then increment j by 1. What we're going to check is if array at index of j is less than our pivot. If one of these elements is less than our pivot, we want it on the left-hand side of our pivot. Any numbers larger than our pivot should be on the right-hand side. So we will increment I by 1 and do a basic variable swap. And we'll need the help of a temporary variable. Int temp equals array at index of I. Array at index of I equals array at index of j. Lastly, array at index of j equals temp. This is just a basic variable swap. Once all elements that are less than our pivot are on the left-hand side, and all elements that are larger than our pivot are on the right-hand side, what we will do now is increment I by 1, and then insert our pivot into its final resting place with another basic variable swap. So let's copy this code, then paste it, and make a few changes. Int temp equals array at index of I, that's the same. Array at index of I equals array at index of end. Array at index of end equals temp. And that's it. And then make sure you return I at the end. That is the location of our pivot. Then after running this, our array is now sorted via the quicksort algorithm. In conclusion, the quicksort algorithm moves smaller elements to the left of a pivot. We recursively divide our array into two partitions and pass those partitions as arguments recursively into the quicksort function. The runtime complexity of the quicksort algorithm actually varies. In its best and average cases, it runs in big O of n log n. However, in its worst case, it can run in big O of n squared. This is rare, and it occurs if the array is already sorted or close to being sorted. But most of the time, it will run in big O of n log n. And the space complexity of the quicksort algorithm is big O of log n. This is due to recursion. It uses more space than bubble sort, selection sort, and insertion sort, even though it sorts in place. That's because the quicksort algorithm uses recursion. We're adding frames to the call stack, which takes memory. So yeah, that is the quicksort algorithm. If you found this video helpful, please be sure to smash that like button, leave a random comment down below, and subscribe if you'd like to become a fellow bro.